Hello, I'm going to be taking you through an example algorithm called Huffman Coding today, and then showing you how examples like this, of which our resources contain many, connect to the curriculum of the AP Computer Science Principles course. And so I'll begin by showing the main webpage for AP Computer Science Principles. And we'll explore this more through the workshop, but I'm going to click on this link called the course, which is going to tell us all about the AP Computer Science Principles course. And there's lots of information here, but what I want to point out is the 5 big ideas, which you'll hear about in the workshop, either after you're watching this video, if you're watching it in the morning, or perhaps you heard some of this today. So Computer Science Principles is built around 5 big ideas: creative development, data, algorithms and programming, computer systems and networks, and the impact of computing. And each of those are broken down into some knowledge statements and some procedural knowledge skills. And I'm going to show how one of our lessons would teach these concepts, and how you can find our information, our lessons, and use them in your class. So there's amongst the files that we've shared with you or will be sharing with you, there's a number of presentations, and one of the documents is called Cool Resources for Computer Science Principles. And when you click on this document, it's going to bring up a Google Doc that has, again, lots of links in it and information about resources that we've collected that can help you teach computer science principles. It talks about some online coding platforms, which we'll be demonstrating in the workshop, as well as computer science principles and some of the success it's had in general. And from there, we then summarize all the resources in terms of those 5 big ideas. So the first one here you can see is creative development, and then we would get on to data and the other ones as well. The one I'm going to emphasize today is from collections of resources for CSP that other people have put together. And so it's a little bit further down, and it's called Cooperative Learning, which was developed by some researchers in the US and high school teachers as well. And if we click on that link, it's going to take us to another Google folder, and a document called Lesson Plans Final. And within this document, there is a table of contents with dozens of lessons that can be used in your classroom. And what's interesting about these cooperative learning structures, examples, and activities is that a lot of them are done without a computer. And so sometimes teachers are looking for ways to bring elements into the classroom that don't involve just more time in front of a screen or in front of a computer. And so I'm going to show one of these lessons today called Huffman Coding. And Huffman Coding is an example of a compression algorithm. And so I'm going to click on this link, number 19, and that's going to jump us down to the page within this document that describes Huffman Coding. So as I was mentioning there, we can see that this only requires pencil and paper to complete this particular activity. It also tells us the high school where this lesson was developed, by Richard Kick at Newbury Park High School. Below the description of before the description of the activity, it talks about learning objectives and essential knowledge statements. And these relate specifically to computer science principles and the knowledge statements that I was mentioning that each of those big ideas will break down into. This is a little bit of an older document, so it comes from the previous version of computer science principles. However, a lot of the statements here are the same in the new version of computer science principles. And so they're coded based on the older system, but the statements will match a lot of what you'll see in the current curriculum for computer science principles. And so I'm going to skip down to the lesson itself. And here is an example of how we can encode text using something called a Huffman tree. Oops, I So this is a Huffman tree, and this Huffman tree has been created to encode the phrase stars rest, which we can see up on the left-hand side here. And the way the tree is constructed is to minimize the amount of data it takes to communicate this particular statement, stars rest. And that's based on the frequency of the letters. So we can see that the frequency is shown here with, there's one space in stars rest, because textual data, every character has to have an encoding, including spaces. There is one letter A, there is one letter E, there are two R's, there are two T's, and there are two S's. And so with these frequencies, we can see down at the leaves of the tree, we can see that those letters, I know it's a little bit tricky to see just because of the resolution, but we can see that this is the blank node, and then there's the E, and then there's the A, and then there's the S, and the R and the T. And so the way that we would then transmit a message like stars rest in binary is by tracing from the root node at the top. So when we want to encode the letter S, we would write a 0 followed to go to the left, followed by a 1. And so this would output 0, 1 for the letter S. For the letter T, we would find the way from the root to the letter T, which would be a 1 followed by another 1. So 0, 1 encodes the letter S, and 1, 1 encodes the letter T. If we wanted to encode E or A, it will take more bits. So to encode the letter E down here at the bottom, we need to traverse the tree 0, 0, 0, 1. So remember that T and S only took 2 bits to encode, but E takes 4 bits, 0, 0, 0, 1. And so that means that the more frequent characters require less bits. And ultimately, this is going to result in kind of a very efficient way to compress text for a particular phrase. And so a Huffman tree is an example of a data structure. And I've just explained to you the algorithm for encoding characters into it. And I'm going to show you now how to actually create the Huffman tree from this particular example. And so I will use the frequencies that we had from the previous example. And so we will start with a space, and that just has a count of 1. And then we had E, which had a count of 1. A, which had a count of 1, and then we had R, which had a count of 2, T, which had a count of 2, make that a T, and S, which had a count of 3. Now, how do we actually create the tree that we saw on the previous slide there from these frequencies? Well, we follow the Huffman algorithm for creating the actual tree itself. And the way that we create the tree is by selecting the lowest frequency characters and creating a node out of them. And so we can pick the 2 lowest. We can see here that there's actually 3 nodes that all have the lowest frequency of 1. So it doesn't matter which 2 we just pick any 2. And so we'll go with the blank and the letter E, and we will create a new node, and we add its weight together so it becomes a weight of 2. And now we ask ourselves, what's the next 2 lowest frequencies in this tree? And it would be the 2 that's one of the 2's, and the 1 that's with the letter A. So here, and we can actually use any of the 2 values, but just for making it easier to draw, I'm going to use this value of 2 that we created from combining the frequencies of E and the blank. And so the frequency of that node then becomes 3. And then we now have to pick the next 2 lowest frequencies, and I'll pause for a second to have you think, what are the next two lowest frequencies? So we have a frequency of 3 here. We have a frequency of 2 and a frequency of 2. So it's actually these two here. So we have to combine those two. It's critical for the Huffman algorithm to pick the two lowest frequencies to create the next node. And so we have to pick those two. So we make a new node and their frequency becomes 4. Now we ask again, what's the next two lowest frequencies in the tree? And it would be the 3 that we've constructed on the left-hand side here, and the 3 for the letter S. So I'm going to redraw the S tree, or the S node there. So I'll just erase this other one. Okay, and then we will draw this new node that combines those two and has a value of 6. And now we only have 2 nodes left. And so they combine for a value of 10. Okay, and it makes sense that the value of 10 is at the root. That number is not really used for anything, but it's the number of characters that we've encoded. Because remember, the original phrase is stars rest, right up here in the top left hand, near the top of this particular example. So here we've created a Huffman tree, and I'll just mark what we use for left and right. We use 1s to go to the left and 0s to go to the right. And so if we wanted to encode the word C, we would try to find the letter S to start. And so we would go 1 to the left, 0 to the right. So 1, 0 encodes the letter S. And then we want to encode the letter E, and we're going to get to that by going 1, 1, 1, 1, 0. 1, 1, 1, 0. And since we want to use E again, we write down 1, 1, 1, 0. So here we can see in 10 bits, a total of 10 bits, we've encoded the word C. And so if we transmitted this message, these binary values here, someone could decode this message if they had the corresponding Huffman tree as well. Now in the top left, I have sent a message in binary, or I've encoded a message in binary. And so now imagine we've received that message and now we're going to decode it. So this is different than what we just encoded, but imagine we're now the receiver and we're receiving this message. So we'll use the same Huffman tree to decode it. And so we just begin reading from left to right. And so we have a 0 first, so we go down here. And then we go to the left because it's a 1. And we arrive at the letter R. So I'll just erase those lines. And we get the letter R from the first 2 characters. And then we will go back to the root and we follow 1, 1, 0. And we arrive at a leaf, which is kind of a node that has no other nodes below it. So that arrives us at the letter A. And so those 3 characters correspond to the letter A. And then 0, 0, we arrive at the letter T. And so this short message here encodes the word rat. And so this tree is limited to only the characters that were used to encode it, so we can't make any word here. If we wanted to encode a more complicated message or that included other letters, we would have to create a Huffman tree that included those letters. But we would do so from a particular message that we want to encode. And by using this Huffman algorithm, we're actually guaranteed to have the shortest message that's possible in terms of the number of bits that we actually need to transmit in order to communicate this information. So that is how you build a Huffman tree and how you use it to encode or decode information. And so in doing an exercise like this, first of all, again, this can be done with pen and paper. And your students have learned about what we call a data structure, which is what this Huffman tree is, as well as an algorithm, a sequence of steps used to do something computationally. And so we must follow the algorithm exactly correctly, which is traversing the tree when we're encoding or decoding. And then also in creating the tree, remember we pair nodes together based on the lowest frequencies, and we build up the tree that way. And so that's how we do Huffman coding. In addition to the explanation that's here, there's also a lot of great resources that are provided. So I'll click on two of these resources and show them to you. The first one is an introduction from someone at Duke University. And so it uses a phrase called, or go, go, gophers. Pardon me, I'm just going to go back so that was clear. A little bit below the lesson where we did the encoding of the stars rest tree, there is a link from Duke University. And if we click there, it goes into greater detail about why Huffman coding saves data. And as an example of compression, it shows the binary values that are used in the common ASCII encoding, ASCII, and shows how a Huffman encoding, as I've highlighted in blue, is a lot shorter than just using the ASCII code. And so emphasizing that compression aspect. As well, another neat example is the link which is below it, which comes from UBC. And if we click on that one, it takes us to this website here. And so if we put in that same message, stars rest, we can then click build tree, and if you watch, it will show you the algorithm as it builds the tree. So it starts by showing the frequencies and then highlighting the lowest frequencies and building the tree. Oh, I see I made a little mistake there. This is actually case sensitive, so it has the capital S as different than the lowercase s. So that was unintentional on my part. But that's actually kind of an important detail about data, which is different cases are completely different letters. The computer doesn't know that a lowercase s has anything to do with an uppercase s. They are different binary encodings. So this is why we ended up with quite a different looking tree than what we had before. But if I go back and make it a lowercase s and build the tree, then we'll see something very similar to what we had that we made. Because, as we saw a few times in this example, we had a choice of which nodes to create. So there's actually different Huffman trees that can be created, and that's a principle of trees that comes from mathematics called symmetry, which means they are effectively the same tree, but just laid out in a different way. And so this is an example, again, or an online tool that can help your students kind of explore Huffman tree with much longer sentences to see what the Huffman tree would create, and also use it then to communicate messages. So the lesson that we've linked off of our cool resources talks about the vocabulary students will learn, and has different ways the students can work together to sort of send messages to each other and practice Huffman coding, and is a really interesting, has more elaborate activities as well that can be used to teach this concept. So another interesting thing about Huffman coding that I would like to emphasize is that the neat thing about it is that no students will have heard of Huffman Coding. And so sometimes in our computer science classes, one of the challenges we have is that some students have more advanced knowledge of programming, which a lot of people misconstrue as that is computer science. Computer science involves programming, but it is not only programming. And so for that reason, it's great to have examples that sort of level the playing field in our classroom. Huffman Coding will be new to everybody. And for that reason, it can help students who maybe feel that they're lacking some of the other technical knowledge, feel that there's something that they can excel at. And so I mentioned how these knowledge statements up at the top correspond to the knowledge that we want students to have about data, and that's particularly what Huffman tree relate to. Of course, we did have an algorithm involved in creating the Huffman tree and encoding and decoding, so expressing an algorithm. And so the way that that connects with the curriculum of computer science principles, again, if we go back to this page where I emphasize the 5 big ideas, one of the documents on here that we'll spend a lot of time exploring is called the course and exam description, so this CED for short. And within it, there are descriptions of the knowledge, the learning objectives, and the knowledge that we want our students to have as they work through this. And so this is under the big idea of data. And so we can see it's on this particular page we're in within the document. It's part of big idea 2. And if we look at the essential knowledge and the learning objectives, we can see that data compression can reduce the size, the number of bits transmitted or stored. And Huffman coding was an example where we came up with a reliable encoding that stored less information. So it's an example of compression. We conveyed the same message with the Huffman tree as we could have with an ASCII encoding. So it doesn't mean that we have, does not necessarily mean we have less information. We've just communicated it and encoded it more efficiently. And that's really what the heart of data compression is. Finally, there's some other concepts in here that I won't go into great detail at the moment, but we could discuss during the workshop if you do have a question. Another important distinction here is lossless data versus lossy data compression, or lossless data compression versus lossy data compression. So there are compression algorithms that do lose some information, but retain the most important information. And so you may know some examples of this. I'll give you a second to sort of think of some where you may have heard of reduced quality, but still usable information. And so examples of this usually come from audio and video formats, or so whether images or video. So the most common example of a lossy data format that most people would be familiar with is MP3 music, which was really kind of a turning point in technology because it allowed full songs to be downloadable. So this would have been about 20 years ago when this first came up, and people were using MP3s because prior to that, transmitting music over the internet was not feasible because there was too much data in the music. And so a lossy data compression where it lost some of the information, but the song still sounded pretty good. And some people will say that they can tell the difference between an MP3 and a CD or a vinyl record or something. That would be an example of lossy data compression. So this is a way you can use some of our resources, such as the cooperative learning example that I've demonstrated here. There's dozens of examples there. And through the statements that are included in each of those lessons, you can relate them to the concepts you'll have to teach from the curriculum, which is summarized in this course and exam description CED document.